Most of us move through life with an assumption so natural we almost never notice it. That you are you, once. A single, unrepeatable thread of awareness, beginning at birth, ending at death, and never woven again into the fabric of reality. We talk about one life to live, as if the universe itself signed a contract with that phrase. And our everyday experience of time encourages it. The past feels sealed. The future feels open. The present feels like a narrow ledge we stand on, watching moments fall away behind us. In that rhythm, it seems obvious that existence is a one-way journey. Intuitive, comforting, sometimes frightening, and yet rarely examined with the cold, quiet tools of physics. Because when you lift your eyes from the human calendar to the cosmic one, the scale changes everything. The observable universe holds hundreds of billions of galaxies, each with billions of stars, scattered across distances so large that light takes years, centuries, and eons just to cross the emptiness between them. And time is not merely days and decades. It is the slow burn of stars over billions of years, the long drift of galaxies, the deep future where familiar constellations dissolve. On those scales, our instincts about rarity begin to wobble. In a universe that vast and that old, the difference between never and not yet can become strangely difficult to feel. Things we label as unique might behave differently when the stage is almost unimaginably large and the play runs for almost unimaginably long. Then comes the first hint from mathematics, soft but unsettling. Physical reality, as far as we can tell, is built from particles and fields, atoms, electrons, quarks, arranged into patterns. A mountain is a configuration. A cloud is a configuration. A book, a heartbeat, a whispered thought, also configurations. Even a human brain, with all its memories and sensations, can be described as a particular arrangement of matter and energy in a particular state. Complex beyond comprehension, yes, but still finite. Not infinite ingredients. Not infinite possibilities in any practical sense. Just an enormous, specific arrangement of a finite set of pieces. And finite systems have a peculiar relationship with time, when time becomes effectively endless. In physics, there are quiet ideas, almost like whispers in the background of thermodynamics and statistical mechanics, that suggest a system can, under certain conditions, wander through its possible states, and given enough time, return close to where it started. Entropy usually pushes things toward disorder, toward spreading out, toward forgetting the past. And yet in the mathematics of large but bounded systems, recurrence can appear. The suggestion that a state once visited is not necessarily gone forever, not even guaranteed to return in any time frame a human mind can hold comfortably, but not forbidden. So the strange idea begins to emerge, not as a fantasy, but as a question with equations hiding behind it. If the universe continues long enough, could the exact configuration that forms you appear again? Not just someone similar, not a near match, but the same arrangement down to the finest physical details, the same brain state, the same pattern that produces the feeling of being you. In the time ahead, we'll wander through the Poincaré Recurrence Theorem, entropy, the eerie notion of Boltzmann brains, and the colossal timescales required for such ideas to matter at all. And if you enjoy quiet explorations of cosmic mysteries like this, you can like the video and subscribe, and we'll keep drifting together through these deep questions, slowly and carefully. Because once you let this possibility in, even for a moment, it lands like a quiet intellectual shock. What if existence is not a singular miracle, but a statistical pattern, something that can, in principle, reappear when the universe has had enough time to reshuffle its pieces? What if mathematics doesn't merely allow repetition, but hints that certain configurations must eventually return? It's a gentle thought, and an unsettling one, that the universe may not allow truly unique moments. But before we can ask whether you might appear again somewhere in the future of the cosmos, we first need to understand what a human life actually is, in the language of physics. To speak about a human life in the language of physics is to begin with something almost embarrassingly simple. You are matter. Not merely matter in the poetic sense, but matter in the strictest scientific sense. A particular collection of particles, borrowed from the Earth, borrowed from ancient stars, held together for a while by chemistry and temperature and time. And when we look closely enough, when we keep zooming in past skin and bone and blood, past cells and organelles, past molecules, we arrive at atoms. A human body is in rough order of magnitude an arrangement of around 10 to the 28 atoms. That number is so large it doesn't fit naturally into the mind. 10,000 trillion atoms, and then some. Carbon and oxygen, hydrogen and nitrogen, calcium and phosphorus, trace metals in tiny, meaningful amounts. Each atom is not especially rare. In fact, the universe is full of them. The wonder isn't the atoms themselves. The wonder is the arrangement. Because what makes you you is not that your atoms are special, but that they are organized in a very particular way, at a very particular moment. The same kinds of atoms can be part of air one day, part of a leaf the next, part of a muscle years later. Over time, even within your own body, the specific atoms are exchanged. You breathe them in, you breathe them out, you eat them, you shed them. The body is less like a statue and more like a river, holding its shape while its contents flow. And yet, despite that constant turnover, your identity feels stable. You feel like one continuous self. That stability points us toward an important idea. Identity emerges from structure, from organization, from relationships between parts, not from some mystical stamp of uniqueness pressed into the matter itself. In physics and chemistry, structure is not an abstract metaphor. It is a real, describable thing. A molecule is not water because it is made of hydrogen and oxygen in general. It is water because 2 hydrogen atoms and 1 oxygen atom are arranged in a specific geometry, with specific bonds, behaving in specific ways. Change the arrangement and you change the substance. In the same way, a body is not you because it contains carbon and calcium. It is you because those atoms are arranged into cells, into tissues, into organs, into a living system that maintains itself, repairs itself, and interacts with the world in a consistent pattern. And here, quietly, mathematics enters the room, because arrangements can be described, they can be counted in principle, they can be represented as configurations, positions, connections, states. Even if the true description is unimaginably complex, the idea is simple and deeply scientific. A physical structure is information, a pattern, something that at least in theory can be expressed in the language of numbers. And if your body is an arrangement of atoms, then the most identity-defining arrangement within that body is concentrated in one place, the brain. The brain is not just another organ, it is a living network, a shifting landscape of connections and signals. Around 86 billion neurons, depending on how you count, each one a biological cell specialized for communication. They reach out with branching structures like trees growing in the dark, and they connect through synapses, tiny junctions where chemical and electrical signals pass. But the neurons alone are not the story. A pile of neurons is not a mind, any more than a pile of transistors is a computer. What matters is the pattern of connections, the wiring diagram, the strengths of synapses, the timing of signals, the way activity flows through the network like weather moving through an atmosphere. At any moment, your brain is alive with electrical rhythms, waves and pulses, oscillations and spikes. Some are slow and soothing, like the gentle roll of sleep. Others are sharp and fast, like the focused edge of attention. These patterns are not random. They are shaped by your senses, your thoughts, your history, your expectations. They are shaped by the world, and by the world's imprint on you. Memories, in the modern scientific view, are not stored like photographs in a vault. They are distributed patterns. A memory is a tendency for a network to recreate a certain activity when prompted. A personality is not a single thing inside the skull. It is a persistent style of processing, a stable set of biases, responses, preferences, and emotional rhythms emerging from physical structure. When you learn, synapses change. When you practice, circuits become more efficient. When you grieve, certain pathways deepen, others quiet. When you fall in love, the brain's chemistry reshapes attention and desire and meaning. Experience doesn't just happen to you, it physically alters you. And consciousness, whatever else it may be, whatever mysteries still surround it, appears deeply tied to this living pattern. The evidence points again and again to a dependence on configuration. Change the brain's chemistry, and consciousness shifts. Damage a region, and aspects of the self can vanish or transform. Stimulate a small area with electricity, and a person may feel a sudden memory, a sudden urge, a sudden emotion rising from nowhere. This is not said to reduce you to something cold or mechanical. It is said to locate you, to place you within the natural world, where causes have effects, where structure gives rise to experience, and where identity is not an untouchable ghost, but a pattern carried by matter. And once we begin to see the brain as pattern, another idea becomes possible, an idea that will matter later when we talk about recurrence and probability. Identity can be understood as information. Not information in the casual sense, like trivia or facts, but information as physics uses the word, a description of a system's state, a way of distinguishing one configuration from another. The particular arrangement of neural connections, the specific strengths of synapses, the distribution of neurotransmitter receptors, the learned pathways that shape your habits and your sense of self. All of it is encoded in the physical structure of the brain. You can imagine it like a vast biological data structure, written slowly over time, not in letters, but in molecules, not in files, but in networks. Your childhood, your language, your fears, your favorite music, the face you recognize in a crowd, the way you interpret a stranger's tone of voice. These are not floating in some separate realm. They are embedded in the physical configuration of your nervous system. And like any physical information, it is limited. Not limited in a way that makes you small, but limited in the mathematical sense that a finite amount of matter can only encode so many distinct states. Each neuron can be in different levels of excitability. Each synapse can have different strengths. The combinatorial space is enormous, so enormous that it dwarfs everyday intuition. But enormous is not the same as infinite. Your brain contains a finite number of particles. Your body contains a finite number of particles. Even if we can't possibly list all the microstates that could correspond to you, the important point is that the number of possible configurations is still a number. A staggeringly large number, but a finite one. And this is where a subtle psychological obstacle appears, because human intuition rebels against the idea that the self can be a countable configuration. We tend to experience individuality as absolute, as cosmically singular, as if the universe has never produced, and could never again produce, anything like this precise inner world you inhabit. That feeling makes sense. It is not foolish. It is deeply human. Part of it may be evolutionary. A mind that treats itself as distinct, valuable, irreplaceable, is a mind motivated to protect itself, to preserve its body, to defend its social position, to avoid danger. A strong sense of personal uniqueness is useful to a creature trying to survive in a world of threats and competition. And part of it is emotional. You are not just a pattern in the abstract. You are the one who feels, the one who remembers, the one who suffers and hopes. From the inside, your consciousness is not a configuration, it is a presence. It is the only place in the universe where you directly encounter reality. So it's natural that the idea of repeatability feels insulting, or eerie, or impossible. Natural that we reach for something beyond physics to explain why this particular I seems so unrepeatable. But there is a difference between emotional uniqueness and physical uniqueness. Emotionally, your life is unrepeatable because it is yours. Because it is woven through your relationships, your context, your perspective, your moment in time. There will never be another first time you heard your own name, another first breath you took, another exact sequence of conversations and choices and accidents that led to this precise present. Yet physically, the claim of absolute uniqueness is a stronger claim than it seems. It is the claim that the specific configuration that constitutes you cannot occur again anywhere, ever, under any circumstances, and physics, quietly, does not naturally grant that claim. Physics is comfortable with patterns repeating. It is comfortable with atoms assembling and disassembling, with molecules forming the same shapes again and again, with crystals repeating lattices over vast distances, with waves cycling through familiar forms. In fact, much of science is built on the idea that nature has habits. So to understand the finite nature of physical self, we need to step back from human emotion for just a moment and look at how physics treats any finite system. In physics, if you have a system with a finite number of particles, confined to a finite region, with finite energy, then the system has a finite number of possible states, at least when you account for the fact that there are limits to how finely distinct states can be, especially when quantum mechanics enters the picture. This is where the concept of phase space appears, a tool from statistical mechanics that can feel abstract at first, but is actually a gentle idea. Phase space is a way of mapping all possible states of the system. If you have a single particle, you can describe its state by its position and momentum. Phase space for that particle is a space where each point represents one possible combination of position and momentum. For many particles, phase space becomes unimaginably high-dimensional, a vast mathematical landscape where every possible configuration of the system corresponds to a point. Your body, in this language, is a region in phase space. Your brain is a region in phase space. A living person is not one fixed point, but a trajectory, moving through a sea of possible states guided by physical laws, constrained by energy, temperature, chemistry, and environment. Now, the number of possible states in that phase space is so large that it can feel like infinity. But mathematically, feels like is not a category. A number can be so huge that no human lifetime could write it down, that no computer could enumerate it, that no imagination could truly picture it, and still be finite, still be bounded, still be in principle countable. This matters because finiteness changes the rules of the game. In an infinite space, you can always insist that something might never occur. In a finite space, recurrence becomes a mathematical temptation. Not a guarantee yet, not in the way we usually speak of guarantees, but a pressure, a quiet pull toward repetition. And when we widen our view beyond the body and brain, the universe itself begins to look like an endless workshop of configurations. Every star is an arrangement of atoms. Not just a glowing ball, but a structured system. Layers of plasma, gradients of temperature and pressure, nuclear reactions in the core, magnetic fields twisting through the surface. Every planet is an arrangement too, shaped by gravity and chemistry and collisions. Every cloud of gas in interstellar space is an arrangement. Every grain of dust, every ice crystal drifting between the stars. Biological organisms are arrangements of atoms that have discovered a special trick. They maintain their pattern by consuming energy. They preserve a certain structure against the natural tendency toward disorder, for a time, by constantly exchanging matter with their surroundings. Life is a pattern that keeps itself going, and the universe is not static. It is a ceaseless engine of rearrangement. Stars fuse light elements into heavier ones, then die and scatter those elements outward. Supernovae seed space with iron and gold and the raw materials of rock and blood. Planets form, break apart, form again. Asteroids collide. Oceans evaporate and rain down. Carbon cycles through air and stone and living tissue. Over billions of years, matter is shuffled again and again, like cards in an unimaginably large deck. And crucially, the laws of physics do not contain a rule that says this exact configuration may happen only once. They contain conservation laws, symmetries, probabilities, constraints. They say what is allowed and what is forbidden. They do not, in general, forbid repetition. If a configuration is physically possible once, it is physically possible again, provided the right conditions occur. Of course, conditions matter. The universe is not obligated to recreate the same thing. The number of possible arrangements is so vast that the overwhelming majority will never be realized in any given region, in any given time span. But the door is not locked by principle. It is only made narrow by probability. And now, gently, we arrive at the bridge we need for everything that follows. If you can be described as a finite configuration of matter, if identity is at least in part information encoded in physical structure, and if physical systems have a finite number of possible states, then the appearance of any particular configuration becomes a question that mathematics knows how to ask. Not as destiny, not as mysticism, as probability. In everyday life, we treat rare events as effectively impossible, not because they truly cannot occur, but because our timescales are short. Our horizons are small. If something has a 1 in a trillion chance of happening in a day, you feel safe ignoring it. But the universe does not think in days. The universe has time measured in millions of years, billions of years, perhaps far more. It has vast arenas where events play out in parallel. Countless planets, countless chemical experiments, countless chances for atoms to fall into patterns. And in such enormous spans of time and space, the meaning of rare begins to soften. A rare event is still rare, but given enough trials, even the rarest allowable configurations have more opportunities to appear. This is the quiet logic that statistical mechanics whispers into cosmology. That probability, given enough time and enough reshuffling, can begin to feel like inevitability. Not because the universe wants something to happen, but because the universe keeps trying over and over, without intention, without fatigue. And if the something we are talking about is a configuration that corresponds to a living human mind, to the informational pattern that you call yourself, then the question becomes both chilling and strangely soothing. Not could it happen, but what does finiteness imply when the cosmos has enough time to explore its own possibilities? For now, we don't need to answer that. We only need to hold the foundation steady, that a human being, in the language of physics, is not an infinite mystery. A specific pattern of matter and information, intricate beyond comprehension, but still grounded in particles and laws. And once we begin to think of existence as a finite configuration of matter, a surprising mathematical principle begins to quietly emerge. That principle begins with time itself. Not the time we feel in our bones, measured by heartbeats and sunsets, but time as a vast mathematical stage, where moments can stretch far beyond intuition. Because there's a subtle difference, quiet but crucial, between a time that is merely enormous and time that is truly infinite. 1 trillion years is a long time, long enough for familiar constellations to dissolve, for galaxies to drift and collide, for the bright, busy era of stars to thin into something older and dimmer. And yet 1 trillion years is still a number. It has an end. If you could count it, even impossibly slowly, you would eventually reach the final digit. Infinity is different. Infinity is not just a really big number. It is not the biggest number. It is the absence of an edge. And cosmology, when it whispers about the far future, often stands right on that boundary between the unimaginably large and the truly endless. We're already accustomed to thinking in billions. The universe is about 13.8 billion years old, a figure that feels abstract until you remember that every single second of your life is a tiny fraction of that cosmic history. But cosmology doesn't stop at billions. It speaks calmly of trillions, quadrillions, and beyond. It considers the slow fading of stars over tens of trillions of years, and the gradual cooling of everything, as if the cosmos itself were exhaling, stretching towards stillness. Some theories go further still, imagining eras where only the longest-lived remnants remain, faint embers of dead stars, drifting planets without suns, black holes evaporating over timescales so vast that even the word age begins to lose meaning. In these pictures, time becomes less like a river and more like an ocean, deep, dark, and wide enough to swallow any human scale. And then, beyond even those long, cold epochs, there is the question that mathematics loves to ask. What if time doesn't stop? What if the processes of physics, particles moving, fields shifting, energy rearranging, continue not for a long while, but forever? Not merely across unimaginable durations, but across a duration that never ends. If you allow that kind of time, you invite a strange new kind of logic. Because in an endless sequence, patterns have more opportunity than we instinctively grant them. In an endless sequence, coincidence has room to become law. And this is where a theorem, quietly proven in the language of mathematics, begins to glow with unsettling possibility. In the late 19th century, Henri Poincaré discovered something that sounds almost like a cosmic promise. The Poincaré Recurrence Theorem says in essence that certain systems, if they are finite and if they are left to evolve long enough, will eventually return arbitrarily close to their initial state. Not exactly the same necessarily, not in a neat, scheduled cycle like a pendulum, but close enough that for all practical purposes, the system can look as though it has come back to where it started, even if it wandered through a vast wilderness of intermediate states to get there. To understand what that means, imagine a closed physical system, sealed away from outside influence, no energy leaking in, no energy leaking out. Its total energy remains bounded. Its number of possible configurations, while perhaps enormous beyond imagination, is still limited by the finiteness of the system, the amount of matter, the volume, the constraints. In such a system, the theorem tells us that the trajectories of motion through state space, the abstract map of every possible configuration, cannot keep discovering truly new territory forever. Eventually, as time stretches on, the system is forced by the structure of mathematics to revisit neighborhoods it has already occupied. It's a little like walking through a gigantic library where every book is a possible arrangement of the system. You can wander for a very long time, pulling down new volumes, reading pages of strange and unfamiliar order. But if the library contains only a finite number of books, and you never stop walking, then sooner or later, you must return to a shelf you've seen before. You must pick up a book you've already opened, even if the library is so large that you could explore for longer than the lifetime of stars. Finiteness plus endless time makes repetition unavoidable. The catch, of course, is the timescale. Poincaré recurrence does not mean you will see the system return within any reasonable era. The recurrence time can be so staggeringly long that it makes the age of the universe feel like the blink of a sleeping eye. It is not a practical prediction. It is a mathematical inevitability, conditional on the system being closed, finite, and allowed to run for long enough. And long enough here is a phrase that hides a cliff edge, because when we apply this kind of thinking to physical matter, especially to the chaotic dance of countless particles, we step into the world of statistical mechanics, where recurrence becomes not just a theorem about abstract states, but a story about probability. In statistical mechanics, a system is not described particle by particle in perfect detail. Instead, we speak in terms of ensembles and distributions, the likely arrangements, the typical behaviors, the overwhelming majority of states that look a certain way. We accept that particles are always moving, colliding, vibrating, exchanging energy. Even in a quiet room, even in a block of solid metal, atoms are not still. They jitter and sway in their places. They explore configuration after configuration, like a restless crowd shifting positions in an endless slow-motion choreography. Now, the number of possible microscopic configurations in a modest amount of matter is beyond comprehension. A glass of water contains on the order of 10 to the 25 molecules. The ways to arrange their positions and velocities within the constraints of energy and volume are so numerous that writing the number down would be an act of pure symbolism, not understanding. But the key idea is this: if the system is finite, then the total number of distinct microscopic states consistent with its constraints is finite too, even if finite here means a number so huge it might as well be an entire universe of digits. As time passes, the system moves from one microscopic configuration to another. It does not choose them with conscious intention, of course. It follows deterministic laws at the microscopic level, classical laws in one approximation, quantum laws in a deeper one. Yet from the perspective of large-scale behavior, it often looks like a kind of sampling. The system explores its available states, and because there are only so many states to explore, the logic of repetition begins to press in. Over long enough durations, certain patterns must repeat, not because the universe is aiming for them, but because wandering through a finite set forever means revisiting points. In probability theory, this is a familiar theme. Given enough trials, outcomes with non-zero probability appear again and again. The more time you have, the more thorough the exploration becomes. Patterns that seemed like one-time miracles become not only possible, but expected. Recurrence in this statistical view is like shuffling a deck of cards. Each shuffle produces a new arrangement. Most arrangements are unfamiliar. Some will never be seen in a human lifetime. But if you shuffle long enough, if you never stop, then even the rarest arrangement is not protected by its rarity. It is merely waiting behind a wall of time. And here, the gentle calm of mathematics begins to reveal its most unsettling feature. The wall of time can be unimaginably thick. Because when physicists estimate recurrence times for realistic systems, the numbers that appear are not just large, they are alien. For a simple gas in a box, recurrence times can already be so long that they dwarf the age of the universe. And for systems with many particles, systems anything like the complexity of planets, biospheres, brains, civilizations, the timescales explode into a regime where everyday language collapses. You may have heard of numbers like a Google, 10 to the power of 100, a 1 followed by 100 zeros. It's already far beyond any physical counting. But recurrence times often involve something far more extreme, numbers stacked in towers of exponentials. One way these estimates emerge is through entropy, which is essentially a measure of how many microscopic configurations correspond to a given macroscopic state. The higher the entropy, the more ways the system can be arranged while still looking the same at large scales. A high entropy state is not a single arrangement, it is a vast ocean of arrangements. If a system has an entropy S, then the number of microscopic states compatible with its constraints is roughly proportional to something like e raised to the power s. That exponential growth is merciless. Even modest increases in entropy produce astronomical increases in the number of states. Recurrence time, in very rough terms, can scale with the number of available states. The more states there are, the longer you might have to wait to return close to a specific one. For macroscopic systems, S is enormous. Some e raised to the power s becomes a number that is not just big, it is a monument to bigness. This is where expressions like 10 raised to the power of 10 raised to the power of 50 begin to appear in recurrence discussions. A 1 followed by 10 to the power of 50 zeros. Not 10 to the power of 50, which is already far beyond the number of atoms in the solar system, but a 10 raised to a power that itself is 50 digits long. Try softly to feel what that means. If you wrote zeros at the pace of 1 per second, you would not finish in the lifetime of the universe. You would not finish before stars burned out. You would not finish before galaxies thinned into darkness. You would not finish before black holes evaporated in their slow, whispering way. You would not finish before any familiar era of cosmic history ended, because you would still be writing the exponent. Recurrence times like these exceed the lifetimes of stars and galaxies so completely that comparison becomes almost meaningless. And yet, they are still finite. That detail matters, because if recurrence time is finite, however grotesquely large, then given infinite time, it is not a question of if, it becomes a question of when, repeated endlessly. But there is another concept equally important that seems at first to argue against recurrence, a concept that shapes our everyday experience so deeply that it feels like a law written into reality itself: entropy. Entropy is often described as the tendency toward disorder, but it's more precise and more haunting than that. Entropy is the tendency of systems to move from less probable arrangements to more probable ones, from special, constrained configurations to typical, unconstrained ones, from the rare to the common. A shattered glass does not reassemble itself on the kitchen floor because the number of ways to be shattered is vastly larger than the number of ways to be whole. The whole glass is a low-entropy configuration, highly specific, highly ordered, requiring an extraordinary coordination of positions and bonds. The shattered glass corresponds to an enormous number of microstates, countless ways for fragments to lie scattered. And because systems tend to drift into the vast regions of state space that contain more microstates, entropy tends to increase. That increase is what gives time its arrow, its feeling of forwardness. We remember the past, not the future, because the past was lower entropy, more structured, more constrained. The future, statistically, is more spread out, more mixed, more typical. This is why recurrence can sound paradoxical. If entropy tends to increase, how can a system ever return close to its initial state? How can it ever revisit a lower entropy configuration? The answer is gentle, but profound. Entropy increase is overwhelmingly likely, but not absolutely guaranteed in every tiny interval. The second law of thermodynamics is statistical. It speaks in the language of near certainty, not logical impossibility. In a high entropy state, the system is in the most typical region of its state space. But even there, fluctuations are possible. Small, local decreases in entropy happen all the time, tiny, transient patterns emerging and dissolving. In the microscopic world, thermal motion is a ceaseless lottery of arrangements. It is just that large decreases in entropy are so unlikely that in human timescales they never appear. Never, in practice. But mathematics has a way of making in practice feel less solid than we want it to be. If the system continues forever, then even the most unlikely fluctuations are not forbidden, they are merely rare. And rarity, in the presence of endless time, is a fragile shield. So now let's drift into an even quieter place, the cosmic void. When we imagine the far future, we often picture emptiness, space expanding, matter thinning, galaxies slipping beyond one another's horizons, a universe that becomes colder and darker, approaching a kind of heat death where everything is spread thin, energy differences smoothed out, and nothing much happens. And yet, Even in that emptiness, physics does not truly stop. In statistical physics, thermal fluctuations are the spontaneous, random deviations from equilibrium that occur because particles and fields never hold perfectly still. If a system is at some temperature, then energy is always jostling around. Even in equilibrium, there is motion, tiny, restless rearrangements. In an ordinary gas, fluctuations might momentarily produce a slightly denser region or a brief pressure difference before it dissolves back into average behavior. In a vast, thin cosmic environment, fluctuations might be incredibly subtle, but the principle is the same. If there is any mechanism for randomness or chaotic exploration of states, then improbable configurations can, in principle, appear. And here the imagination can become almost too powerful, so we keep it anchored to the math.
The math says, if there is a non-zero probability of a configuration arising, then given enough opportunities, enough trials, it will occur.
A rare arrangement is like a specific hand in a card game. Draw once, and it may never appear. Draw a million times, and it might still be absent. Draw endlessly,
and eventually it arrives, not because the universe is aiming for it, but because there is no longer any final draw where the story ends. This is the quiet suggestion behind ideas like spontaneous self-organization, or even the eerie thought experiments that float at the edge of cosmology. Moments when out of a sea of high entropy, a low entropy island briefly forms. Particles aligning, energy concentrating, structure assembling by chance. The probability of complex structures forming by random fluctuation can be unimaginably small. The universe is not likely to assemble intricate patterns out of nothing in any short span of time. The odds may be so low that even waiting longer than the current age of the universe would change almost nothing. But with infinite time, almost nothing becomes a different kind of statement, because infinity does not bargain, infinity does not get tired, infinity does not run out of chances. And this is where probability begins to feel like destiny. In everyday life, we treat low probability events as effectively impossible. You are not likely to be struck by a meteorite. You are not likely to win a lottery 100 times in a row. You are not likely to see a shattered glass leap up and reform itself on the table. The universe on the human stage is stable enough that we can build our lives on these assumptions. But mathematics draws a line between impossible and improbable, and it is an uncompromising line. If an event has zero probability, if it is forbidden by the laws of the system, then no amount of time will bring it about. But if an event has non-zero probability, even if that probability is so tiny it can hardly be written, then the logic of repeated trials begins to lean on it. In an infinite sequence of trials, events with non-zero probability occur not just once, but infinitely many times. This is not a poetic claim. It is a consequence of the way probability behaves when the number of opportunities has no end. So if a finite system continues to evolve through its allowed configurations, and if the system has any mechanism, deterministic chaos, quantum randomness, thermal motion, that effectively explores those configurations across time, then recurrence is not merely a dreamy metaphor. It becomes a mathematical expectation. Not on a schedule you can mark on a calendar, not in a way that offers comfort or control, but as a deep property of finite state spaces and endless duration. And suddenly, the earlier idea that existence is a finite configuration of matter and information finds itself connected to a larger, colder framework. Because if you are, in some sense, a particular arrangement within a finite set of possible arrangements, then the question of return is no longer purely philosophical. It becomes combinatorial, statistical, almost mechanical. The universe, in this view, is not a one-way story that forever writes new chapters and never looks back. It is a system wandering through its possible pages, and given enough time, it must, at least in principle, turn back toward familiar sentences. Of course, all of this depends on conditions. Whether the universe is truly a closed finite system, whether its state space is bounded, whether time is infinite, whether quantum gravity or cosmological expansion changes the rules in ways we don't yet understand. These are deep questions, and we will approach them slowly, with care. But for now, just let the mathematical shape of the idea settle. Finite possibilities, endless time, and the inevitability of revisiting what has been visited before. Not because the universe remembers, not because it repeats with intention, but because, in the long run, mathematics can be more patient than any physical process we've ever witnessed. And if recurrence truly governs the behavior of matter,
then the universe itself may behave less like a straight line and more like a cosmic deck of cards, endlessly reshuffled. Imagine that deck now, not in human hands, but in the quiet grip of physics itself. Every particle in the universe becomes a kind of card. Not a flat rectangle of paper, but a tiny token of possibility, a unit that can be here or there, moving this way or that, carrying this energy, holding that spin, occupying this state rather than another. And the universe, with its ceaseless motion, its collisions, its expansions and contractions, its gentle drifting and violent eruptions, becomes the shuffle. In an ordinary deck, shuffling doesn't create new cards. It only rearranges what already exists. And that's the first calming twist of the metaphor. Much of what happens in the cosmos is not the creation of brand new ingredients, but the endless rearrangement of the same basic ones. Hydrogen and helium, forged into heavier elements in stars, scattered again, gathered again, locked into planets, dissolved into dust, and returned to the interstellar sea. A shuffle is a distribution of outcomes across time. If you shuffle once, you get one ordering. Shuffle again, you get another. Over many shuffles, the deck explores its possible arrangements. Some arrangements are more likely than others, not because the deck is biased in a human sense, but because some patterns can be achieved in vastly more ways. In probability, this is a quiet law. Outcomes distribute themselves, and over long enough time, the distribution begins to reveal its shape. So if the universe is shuffling matter, then every moment is like a draw from a cosmic deck, a deal onto the table of space-time, a new hand, a new pattern, a new configuration of particles, some mundane, some astonishing. And in that sense, existence can feel like a lottery, not just because it is rare, but because it is one particular ticket pulled from an unimaginably large drum. The cosmic lottery doesn't draw once and stop. It draws again and again and again, for as long as the shuffling continues. The question becomes less emotional and more mathematical, less why me and more how many possible hands are there, and how long does the dealing go on. Now, if the deck were truly infinite, if there were infinitely many distinct cards, or infinitely many positions they could occupy, then the metaphor dissolves into something too open-ended to grasp. But physics, at least as we understand it, keeps offering us boundaries, limits, finite capacities, discreteness where we once assumed smooth continuity. Consider something intimate, the human brain. It feels infinite from the inside. A mind can imagine endless landscapes, recall countless memories, generate new thoughts without apparent limit. But the brain is a physical object. It has a finite number of atoms, a finite volume, a finite range of energies it can hold without tearing itself apart or freezing into stillness. Its physical state, its detailed arrangement of molecules, ions, electrical potentials, neurotransmitter concentrations, microstructures, must be one state among a vast but bounded set. Even if we allow the number to be so large it defies comprehension, the key word remains finite. This is the strange comfort and the strange terror of combinatorics. When you have a system made of many parts, each part with multiple possible states, the number of total arrangements grows explosively, not linearly, but like an avalanche of numbers. If you have 100 switches, each of which can be on or off, you don't have 200 states. You have 2 to the power of 100, a number so large it already feels like science fiction. And the brain is not made of 100 simple switches. It is made of perhaps tens of billions of neurons, each with complex internal chemistry and connections, each influenced by surrounding cells and signals. Even if we simplify brutally, even if we reduce the brain to a coarse description, neurons firing or not firing, combinatorics immediately launches us into a realm of numbers that can't be held in a single mind. And yet, no matter how tall the tower becomes, it is still a tower with a top. It is not infinity. The same is true for a human body, for a planet, for a star, for any finite region of space with finite energy. There is only so much information it can physically contain, only so many distinguishable configurations it can reliably hold. This idea appears in different forms across physics, sometimes as a bound on entropy, sometimes as limits related to quantum mechanics and gravity, but the mood is consistent. The universe allows enormous variety, but not unbounded variety in a bounded space. So you can say, without needing to know the exact number, that a human being corresponds to a set of possible physical arrangements. And that set, while absurdly vast, is not endless. And once you accept that, the library opens. If a finite system has a finite number of possible states, then all those states can be imagined as pages in an immense catalogue. Not a library built of wood and stone, but a library built of possibility. Physicists have a name for this catalogue. They call it phase space. Phase space is one of those concepts that sounds abstract until you realize it is simply a map of everything a system could possibly be. For a simple object, say a swinging pendulum, its phase space might be described by its position and its velocity. Every point in that space represents a complete state of the pendulum. And as time passes, the pendulum traces a path through its phase space, like a quiet pencil drawing curves on invisible paper. For a more complex system, phase space becomes unimaginably high-dimensional. Every particle contributes coordinates, positions and momenta, internal states, fields and more. The number of dimensions blooms beyond anything we can visualize. But the idea remains beautifully calm. The system moves through its own possibility space, and in that view, the universe is not merely happening, it is traveling. At each moment, the cosmos occupies a particular point in its phase space, one complete description of where everything is and how everything is moving. Then, an instant later, it occupies another point. And the laws of physics, those quiet, persistent rules, guide the trajectory. What matters for our story is not that we can write down the entire phase space of the universe. We cannot. What matters is the philosophical and mathematical implication. If a system is finite in the relevant ways, then its phase space contains a finite number of distinct states, or at least a finite volume of distinguishable states. And if time continues, the system continues to wander. Some regions of phase space might be easy to reach, others might be almost impossibly rare. Some might represent smooth, ordinary arrangements, diffuse gas, lukewarm rocks, random thermal motion. Others might represent intricate structures, crystals, storms, living cells, nervous systems, and minds. But the library includes them all. Every configuration that does not violate physical law sits somewhere in that space, like a book waiting on a shelf. Now, if the universe keeps traveling through phase space, what happens across very long durations? This is where recurrence begins to feel less like a poetic notion and more like a statistical inevitability. In ordinary life, we don't expect exact repetition. The weather does not repeat perfectly. No two waves on the ocean are the same. Even the patterns that seem cyclical, day and night, seasons, tides, are only approximate, drifting with subtle changes. But this is because the timescales we experience are short, and the systems around us are large and complicated. Probability, however, has a different patience. If you have a finite number of possible states, and you keep moving through states, then, under many kinds of motion, returns become unavoidable. Not necessarily returns on a human timescale. Not necessarily returns that look like a neat, obvious loop, but returns in the sense that the system revisits states it has visited before, or states arbitrarily close to them. Even without deep physics, you can feel this with a small example. Imagine a simple lottery machine with only 10 numbered balls. If you draw one ball, replace it, and draw again, you will see repeats quickly. Draw long enough, and you don't just see repeats, you see every number again and again. The rarity of any particular ball is not the question. The question is how long you are willing to wait. Or imagine flipping a coin. A specific sequence, say 20 heads in a row, is extremely unlikely in any short stretch. Most nights you could flip coins until you grew bored and never see it. But the sequence is not forbidden. It has a probability, 1 in about a million. So if you flip long enough, if you keep flipping across a span of time that is large compared to a million, then that astonishing run becomes less like a miracle and more like an appointment. Not guaranteed at a precise moment, but waiting somewhere ahead of you in the fog. In large systems, repetition becomes subtle because the number of possible states is so huge. Yet the principle persists. With enough trials, rare patterns reappear. And with enough time, the universe becomes a stage where not only common structures recur, but even exquisitely specific ones can, in principle, return. This doesn't mean the universe repeats like a simple loop. It means that in the vastness of time, statistical repetition is a natural consequence of finite possibility. And so we arrive at a quietly unsettling thought. Familiar patterns may not be unique. Not because the universe is trying to repeat itself, but because when the deck is shuffled long enough, some hands are dealt more than once, even the hands that feel impossibly special. Now we can finally approach the question that has been hovering at the edge of the room, the probability of you. Let's be gentle with ourselves here, because the numbers can become dizzying, and the goal is not to overwhelm, but to clarify. A human being is not just a pile of atoms. It is a particular arrangement of atoms, assembled into cells, tissues, organs, and, most critically for identity, into a living brain with a specific structure shaped by genetics and experience. The exact microstate of a living person at a given moment would involve astronomical detail. The quantum states of particles, the precise positions and momenta, the chemical states of countless molecules. If we attempted to compute the probability of recreating that exact microstate by random rearrangement of matter, the number would likely be so small that writing it down would be pointless. It would be a 1 followed by more zeros than there are grains of sand on all the beaches of Earth. And then more zeros still. Even if we relax the demand, even if we say, not the exact quantum microstate, just the same functional brain state, or just the same person in a meaningful biological sense, we still face a combinatorial mountain. To build a particular protein from amino acids is already a needle in a haystack. To build a cell with thousands of proteins, each in the right place and timing, is a haystack made of haystacks. To build a brain with its intricate wiring, refined by development and life, is a vastness that laughs at intuition. So yes, by everyday standards, the probability looks like 0. But mathematics has a careful distinction it insists on making. Almost 0 is not 0. A probability can be unimaginably small and still be non-zero. And if it is non-zero, then the only remaining question is the number of trials, the number of shuffles, the length of time the cosmic lottery continues to draw. This is where infinity, if it truly applies, changes the emotional texture of the problem. Because in an infinite sequence of trials, even the rarest non-zero probability event is not merely possible. It becomes inevitable. Not in the sense that we can predict when, not in the sense that it must happen in any particular region, but in the sense that it cannot be excluded.
If the universe has infinite time, or infinite space, or endlessly many opportunities for matter to arrange itself, then the difference between almost never and eventually becomes the difference between a finite story and an endless one. A single lottery ticket almost never wins. But if you buy tickets forever and the lottery is fair, and the drawing continues forever, then a win is no longer a fantasy. It becomes a matter of waiting. And that is the strange logic that begins to surround you. Your particular arrangement, your body, your brain, your living pattern, may be so rare that it effectively never occurs in the portion of the cosmos we can observe. And yet, if the cosmic deck is dealt without end, rarity becomes something like a delay, not a barrier. Still, there is another ingredient in this story, one that shapes the stage on which all these shuffles take place. Entropy. Entropy is often spoken of as a kind of doom, the slow slide from order to disorder, and in a broad sense that's a fair poetic description. Left to itself, a hot object cools. A tidy arrangement tends to become messy. A concentrated resource spreads out. Energy becomes less available to do useful work. But entropy is not simply things get worse. It is a statistical tendency. And within that tendency, local pockets of order can and do appear, especially when there is a flow of energy through a system. A snowflake is order emerging from chaotic molecular motion. A crystal is order. A hurricane is an organized structure, born from heat and rotation. Even a flame has a kind of shape and persistence, fed by chemical energy. Life too is a local pocket of order, not because it violates entropy, but because it participates in it. Living things maintain internal structure by consuming energy and exporting entropy to their surroundings, radiating heat, producing waste, increasing disorder elsewhere, while preserving organization within. And that brings us back to the cosmic setting. Stars are not just lights in the sky, they are entropy machines, colossal furnaces that take simple fuel and produce a stream of energy outward into space. Around some stars, planets form, worlds with surfaces, oceans, atmospheres, chemistry, weather, and time. Planets provide gradients, hot and cold, wet and dry, light and dark, pressure and vacuum. They provide niches where complexity can build,
where molecules can explore their own phase spaces, where structures can persist long enough to replicate. From that perspective, life is not an impossible fluke dropped into a dead universe. It is one of the things that matter does when given energy, time, and the right conditions. Not guaranteed everywhere, not common in every region, but perhaps a recurring pattern. If the universe is dealing hands forever, stars and planets are like tables, where the dealing can actually produce intricate games. Places where the cards can arrange into long chains, self-correcting loops, and systems that remember. And memory is important, because life is not just structure. It is structure that carries forward, structure that copies itself with variation, allowing selection to sculpt complexity over long spans of time. In a universe that allows such processes, the emergence of living patterns may be less like a single miracle and more like a theme that reappears, different melodies, different instruments, but recognizable in its logic. So when we imagine the recurrence of you, it may not require a universe that randomly assembles a human being from dust in a single throw. It may instead involve the recurrence of environments where life arises, where evolution explores, where brains emerge, where minds awaken. The path can be long, winding, and still, in principle, part of the library. Now, let the imagery widen again and soften. Picture the universe as an endless casino, but without noise, without greed, without hurry, just quiet mechanics, the turning of galaxies, the slow dance of gravity gathering matter into stars, the explosions that scatter it again, the formation of new worlds, the chemistry on their surfaces, the deep time in which complexity has room to breathe. Every moment is another deal. Not a deal of 52 cards, but a deal of every particle in a region, every field excitation, every quantum possibility settling into one realized pattern. And then the next moment, another. The deck is shuffled by thermodynamics, by gravitational interactions, by quantum uncertainty, by the relentless unfolding of time. In some hands, nothing interesting happens. Diffuse gas, empty space, radiation fading into coldness. In others, there are sparks. A star ignites, a planet forms, a chemical network begins to cycle. In a very small fraction, perhaps, the game becomes elaborate enough to produce observers, beings who look back at the universe and wonder what it is doing. And you, in this framing, are one outcome among countless possibilities. Not the center of the deck, but a particular combination that happened to land. A hand dealt in one corner of one galaxy, around one star, on one planet with liquid water and protective skies, in one lineage of life that survived long enough to become conscious. If the dealing continues long enough, then even the rare hands return. Not frequently, not predictably, but inevitably, if the number of trials is truly unbounded and the set of possible hands is finite in the relevant way. The universe doesn't need intention, it needs only time and the capacity to keep shuffling. And yet, even as this idea begins to feel like a mathematical spell, there's a gentle shadow at its edge. Because recreating a physical configuration is one thing. Recreating a pattern of atoms arranged like a brain, with the same structure, the same activity, the same stored information, that is a claim about matter. But there is another claim hidden inside the hope of living again. It's not just that a body could reappear, not just that a brain could be rebuilt somewhere in the library of phase space. It's the question of what it would mean from the inside. Because even if the universe can recreate the physical structure of a human being, a deeper question remains about the nature of consciousness itself. Consciousness is a word we use as if it were simple, as if it names a single clear thing. But when we try to place it inside the language of physics, it becomes misty and strangely hard to hold. Physics is wonderfully precise about masses and charges, about trajectories and energies. It can tell you how a photon bends near a star, how atoms bond, how heat spreads, how time dilates. But consciousness is not like a planet you can weigh or a wave you can measure directly. It's not a particle in a detector. It's the felt presence of being, the quiet inner light that notices itself. And that is exactly the problem. Consciousness is both the most intimate thing you know and the most difficult thing to define from the outside. In science, we usually begin with definitions that allow measurement. If we can't measure it, we can't test it, and if we can't test it, we can't refine our understanding. Yet consciousness seems to hide behind every measurement, because it's the very condition under which measurement is experienced. We can describe behaviors, report brain activity, observe reactions, map neural networks, and ask people what they feel. But the raw fact of subjective experience, what philosophers sometimes call what it is like, doesn't appear on a scan the way a tumor does. It appears only as the experience itself. Still, neuroscience has made a powerful case that consciousness is deeply linked to brain activity. When the brain is injured, experience changes. When certain regions are stimulated, perception shifts. When anesthesia alters neural signaling, awareness fades. When sleep changes the brain's rhythms, the world disappears and returns in dreams. The correlations are not subtle, they are overwhelming. If you change the physical state of the brain, you change the mind. This is why many scientists treat consciousness as something that emerges from matter in motion, not as a separate substance floating above the body, but as a pattern, an activity, an organization. Like a hurricane is not a special hurricane particle, but a structure made of air and energy. Like a flame is not an extra ingredient beyond fuel and oxygen, but a dynamic process sustained by chemistry. In that view, consciousness is an emergent structure, not a simple ingredient, but a high-level phenomenon that arises when a system reaches a certain kind of complexity, certain kinds of feedback loops, certain kinds of integrated information processing. It's not that neurons are conscious by themselves. It's that trillions of interactions, arranged in particular ways, might generate a unified field of experience. And yet, even this elegant framing leaves something unresolved, because even if consciousness emerges from physical structure, we still have to ask what that means for recurrence. If the universe rebuilds the structure, does it also rebuild the experience? This brings us to a question that sounds like science fiction, but is really a sharp edge of philosophy and physics meeting in the dark. Imagine a perfect replica of you, not a lookalike, not a copy that behaves similarly, but a true, atomic-level duplication. Every neuron in the same state, every synapse tuned the same way, every molecule in the same place, every ion poised at the same membrane, every electrical potential identical. A physical configuration that matches you so perfectly that from the outside it is indistinguishable. Now ask gently, and without rushing, would that replica be you? Would it share your subjective experience? Would it be the same eye looking out from behind the eyes? Or would it be a new observer, one who merely believes it is you because it contains all your memories and habits and inner narratives, but who is, in some deeper sense, separate? This is the replica question, and it goes straight to the heart of identity and continuity. In everyday life, we assume we persist through time. You wake up and feel like the same person who fell asleep. Your body changes slowly. Your cells replace themselves. Your memories shift and blur. But something seems continuous. We tie identity to an unbroken chain, each moment flowing into the next, each experience connected to the previous one by the ongoing activity of the brain. But duplication breaks that chain. If a perfect copy is created somewhere else, there are now two beings with the same past. Both remember your childhood, both know the same secrets, both feel the same loves and regrets. For a brief moment after duplication, they would even speak the same words, make the same predictions, anticipate the same outcomes. Yet they cannot both be the same singular you, because they will immediately diverge. One will look left, the other right. One will hear a different sound. One will take a different breath. The universe will fork them apart. So which one is you? The question feels unfair, almost mischievous, because it reveals something we usually keep hidden. Identity might not be a single objective thing. It might be a story the brain tells, grounded in continuity rather than essence. Philosophers have wrestled with this through thought experiments for centuries. The teleporter problem is a famous one. A machine scans you, destroys the original, and reconstructs you elsewhere from new atoms arranged the same way. Would you step into it? Would you expect to wake up on the other side? Or would you expect to die, replaced by someone who only thinks they are you? Some argue that if the pattern is what matters, then the reconstructed person is you. Others argue that destruction breaks continuity, and the new being is merely a copy. And some take an even stranger position, that identity is not a deep fact at all, but a convenient label we apply to evolving patterns. In the context of cosmic recurrence, this matters profoundly, because recurrence does not promise continuity. It does not promise a thread that carries you safely through time. It promises only that configurations can repeat. that the universe, given enough time and space, might assemble the same arrangement again. But whether that arrangement contains the same inner light, the same first-person perspective, is the mystery. And to make the mystery even sharper, cosmology offers a thought experiment so eerie that it feels like a whisper from the edge of infinity. The Boltzmann brain. The idea begins with a simple statistical truth. In a vast system, random fluctuations can produce temporary order. In a gas, molecules sometimes cluster more than average, just by chance. In a thermal environment, improbable arrangements occasionally appear, rare, fleeting, but not impossible. Now expand that idea to the universe itself. If the cosmos lasts long enough in a state of near equilibrium, and if random fluctuations are allowed to play their endless lottery, then, so the argument goes, it might be statistically more likely for a single, self-aware brain to fluctuate into existence than for an entire orderly universe like ours to arise. A Boltzmann brain would be a momentary island of structure in a sea of chaos, a brain formed by chance, with neurons arranged just so, perhaps even with a surrounding bubble of supportive conditions, oxygen, temperature, maybe a false environment, just long enough for it to have an experience. And here is the haunting part. If consciousness is tied to physical configuration, then a Boltzmann brain could briefly be conscious. It could open its eyes, if it has eyes. It could feel a thought form, if it has the circuitry for thought. It might even possess memories, because memories are patterns, and patterns could be part of the fluctuation. It could remember a childhood that never happened, recall a life that was never lived, believe it has a history, because the physical structure of memory does not inherently require that the events were real. It only requires that the brain contains the information. For a few seconds, or a fraction of a second, there might be a mind in the void, looking out at nothing, and then dissolving back into randomness. Boltzmann brains are not proposed because anyone wants them to be real. They are proposed because they might be an unavoidable prediction of certain cosmological models. And that is why they are so troubling. Because if a theory predicts that most observers are Boltzmann brains, then it implies that most conscious experiences are delusions, randomly assembled minds with fabricated memories, floating in the dark. It also implies that our own structured universe is statistically unlikely compared to these fleeting observers. This creates a paradox. We do not seem to be Boltzmann brains. Our observations are consistent, stable, law-like, shared with other observers. The world behaves as if it has a coherent past. So cosmologists use the Boltzmann brain problem as a kind of filter, a way to rule out models of the universe that would make such brains overwhelmingly common. In a strange way, the very possibility of a conscious brain appearing from chaos becomes a test of our cosmology. It forces physics to confront the relationship between probability, time, and observation. And it quietly reinforces the theme we've been circling. If consciousness depends on structure, then structure might not need a long history to exist. It might only need to appear, which leads us into an even wider thought. Observers emerging from chaos. We tend to imagine consciousness as something that requires a long evolutionary story, billions of years of chemistry, stars forging heavy elements, planets cooling, oceans forming, life beginning, natural selection sculpting nervous systems, brains growing more complex. And on Earth, that story seems true. It's the path we know. But if the universe is vast enough, and time is long enough, then probability begins to play tricks that feel almost magical. In an infinite or near-infinite setting, rare events are not just possible, they can become inevitable. Not inevitable here, not inevitable soon, but inevitable somewhere, sometime, given enough chances. The emergence of an observer might be one of those events. Not necessarily a human observer, not necessarily carbon-based, not necessarily anything that would fit our expectations. If consciousness is an emergent property of certain kinds of information processing, then perhaps it could arise in substrates we haven't imagined. In exotic chemistry, in plasma filaments, in vast, slow networks of interacting matter, in artificial systems built by other minds, or in fleeting configurations that bloom and vanish like quantum foam. Even if we restrict ourselves to familiar biology, the statistical argument remains unsettling. If the universe can randomly assemble a brain, it could randomly assemble a simpler nervous system. If it can assemble a nervous system, it could assemble a living cell. If it can assemble a cell, it could assemble a replicator. Each step may be fantastically improbable, but improbability is not impossibility. In the deep arithmetic of enormous timescales, probability becomes a kind of creative force. And this is where the idea of recurrence becomes more than a cold mathematical statement. It becomes a question about the inevitability of observation itself. If observers can appear spontaneously, then the fact that you are an observer is not just a personal miracle. It may be an expected outcome in a universe that gives chance enough opportunities to try. Your existence in that view is connected to probability in a direct and almost unsettling way. Not because probability wants you, not because the cosmos is aiming at consciousness, but because once the space of possibilities is explored broadly enough, patterns that allow experience may recur. And yet even if observers can appear, even if a brain can form by chance or by recurrence, the central question remains. To approach that, we have to look closely at what makes you feel continuous to yourself in the first place. Memory. Memory is not stored as a single object tucked away in a hidden drawer. It is distributed across networks of neurons. It is encoded in the strength of synapses, in the patterns of connectivity, in the way certain pathways are more easily activated than others. It lives in chemical changes, in structural modifications, in the subtle tuning of circuits that represent associations. This smell with that place, this face with that name, this pain with that lesson. When you remember something, you do not retrieve a perfect recording. You reconstruct. The brain reactivates patterns, fills in gaps, reshapes the past slightly each time, and those reconstructions become part of the memory itself. Memory is alive. It is a process, not a static archive. Identity is woven from that process. The feeling of me is tied to a narrative the brain maintains, a model of itself moving through time, holding on to a coherent story. Even your sense of being a single subject, one observer rather than many, seems to depend on the integration of information across the brain, binding sight and sound and touch and emotion into one seamless stream. So if a future recurrence recreates your brain exactly down to the last synaptic weight, then it would recreate your memory patterns. It would recreate the narrative machinery. It would recreate the self-model. From the outside, it would behave as you. From the inside, it would likely report being you. It would remember being you. It would look at its hands and feel the ordinary intimacy of ownership. But is that enough to guarantee the same subjective experience? Some thinkers say yes. They argue that consciousness is entirely determined by physical state. If the state is the same, the experience is the same. In that view, two identical brains would not just think the same thoughts, they would instantiate the same conscious moment in the same way that two identical equations represent the same relationship. Consciousness would be a property of the pattern itself. Others are more cautious. They argue that even if the replica has an experience indistinguishable from yours, it is still a separate subject, because subjectivity is tied to the specific physical process unfolding continuously, not merely to the abstract pattern. In that view, two identical brains would host two distinct streams of consciousness, even if those streams begin identical. And still others suggest that the question might be misguided, because it assumes there is a single you that must be tracked like an object. Perhaps personal identity is not a thing that can be transported or duplicated. Perhaps it is more like a flame. It can be relit, it can be copied, it can be sustained, but there is no secret essence that must remain the same. These possibilities aren't just intellectual games. They change the emotional meaning of recurrence. If identical structure guarantees identical experience, then recurrence could be a kind of return, not in memory, not in continuity, but in the literal reappearance of the same conscious moment, blooming again in the cosmic garden. A repeated configuration would not merely resemble you, it would be you, in the only sense that matters, the sense of being. But if continuity is essential, if the I depends on an unbroken causal chain, then recurrence would produce copies who feel like you, but you would not awaken as them. They would be new islands of awareness, separated from you by the void, even if they carry your name and your memories like perfectly forged documents. And if identity is a convenient story rather than a deep fact, then the question becomes less about whether the future being is really you, and more about what we mean when we say I at all. It's here, in this quiet uncertainty, that we begin to see why physicists and philosophers remain divided. Among scientists, there is broad agreement that mental life depends on physical processes.
But there is not broad agreement on what that implies about personal continuity across duplication or recurrence. Some physicists lean toward a straightforward physicalism. Same physical state, same mental state. For them, the universe repeating a configuration would repeat the mind associated with it, because the mind is what the configuration does. Consciousness is not an extra ingredient, it is the activity of the pattern. Others emphasize that physics describes systems from the outside, while consciousness is known from the inside. They point out that no matter how complete our physical description becomes, it might still leave an explanatory gap. Why should any physical process be accompanied by experience at all? Why is there something it is like to be a brain, instead of nothing but computation in the dark? And that gap matters, because if we do not fully understand why consciousness arises, we cannot confidently say what happens under duplication. We can say the replica will behave the same. We can say it will claim to be you. We can say it will have the same memories. But whether you continue, whether the first-person perspective is preserved, is not something current physics can settle. This is the difference between physical duplication and personal continuity. Physical duplication is clear. In principle, an arrangement of matter can be copied. Even if it is practically impossible, it is conceptually well defined. You can imagine the atoms, the fields, the states. Personal continuity is not clear. It is not a measurement. It is not a conserved quantity. It is a lived thread, and it may not be something the universe tracks the way it tracks energy or momentum. Some researchers try to formalize consciousness in mathematical terms: information integration, global workspace dynamics, predictive processing, and other frameworks that aim to connect subjective experience to objective structure. These are serious, ambitious attempts, but none have yet achieved the status of a universal law, the way thermodynamics or electromagnetism has. Consciousness research remains incomplete, and honest scientists admit it. So we stand in a curious place. We have enough knowledge to suspect that structure matters deeply. We have enough mystery to doubt that structure alone resolves the question of who. And now, with all of this in mind, we can let the imagination drift outward, not to escape rigor, but to test what our ideas feel like when stretched across cosmic time. Picture the universe far in the future, not just centuries, not just millions of years, but timescales so long that stars have changed their populations, galaxies have reshaped, and the night sky has become unfamiliar. Perhaps the universe expands forever, thinning and cooling. Perhaps it cycles, perhaps it tunnels into new phases. Imagine that the cosmic dice continue to roll. In that vastness, somewhere beyond any map we can draw, matter collects in a pattern. Not necessarily on a planet like Earth, not necessarily under a sun like ours, but in some pocket of conditions, some rare convergence, atoms arrange themselves into chemistry, chemistry into cells, cells into a nervous system, and a nervous system into a brain. Or perhaps the brain arrives by an even stranger route, a sudden statistical miracle, a fluctuation that assembles complexity without a long prelude. And in that brain, one day, there is a configuration, a pattern of synaptic strengths, of neural firing potentials, of molecular alignments, that matches a human mind that once lived long ago, a mind that worried and wondered and loved and listened to the quiet hum of existence, a mind that asked, in its own era, whether it could ever return. For a moment, whether that moment lasts seconds or decades, there is awareness, and perhaps, inside that awareness, there is a sense of familiarity, a feeling of being a self, a recognition of a world, a memory of a name. A recollection of a life that in this place has not been lived, but is nonetheless present as information. Is that a resurrection, or a new beginning? If consciousness is a recurring phenomenon tied to structure, then the universe could be a stage where minds appear again and again, not as ghosts, not as souls drifting between worlds, but as patterns that re-emerge when the mathematics of possibility allows. In such a cosmos, awareness is not a singular event. It is a theme, a melody that can be played more than once when the instrument is built the same way. And maybe it doesn't happen only to you. Maybe it happens to countless observers scattered across space-time like sparks. Minds that rise, look out, and vanish. Minds that evolve and build and explore. Minds that never meet, yet are linked by the deep logic of recurrence. It's a thought that can feel both comforting and unsettling.
comforting because it suggests that experience is not fragile in the ultimate sense, that the universe can, under the right conditions, host the return of patterns that once existed. Unsettling because it also suggests that you might not be a single thread, but a type of pattern that can be instantiated more than once, with or without any continuity between instances. And perhaps the most mysterious possibility is this, that from the inside, the difference might not even be noticeable. If a mind appears with your memories and your personality and your inner voice, it may feel as though it has always been you. It may feel like waking up after a long sleep, with no awareness of the gap. It may look back on its past and feel the emotional weight of a life it believes it lived. But whether the original you has traveled into that experience, whether there is any meaningful bridge across the void, remains unclear. This is where the science becomes quiet and the philosophy becomes loud, even when spoken in a whisper. Because we can imagine recurrence. We can imagine duplication. We can imagine a universe large enough to replay the same arrangement. But we still do not know what consciousness fundamentally is, in the language that would let us say, with confidence, what repeats and what does not. Maybe consciousness is fully determined by physical structure, and so it returns whenever the structure returns. Maybe consciousness is tied to causal continuity, and so recurrence creates new minds that only resemble old ones. Maybe consciousness is something deeper still, an aspect of reality we have not yet learned to measure, a property that depends not only on arrangement, but on history, on context, on the unfolding of process through time. Physicists, philosophers, neuroscientists, they circle these questions from different angles, building models, proposing tests, refining concepts. The universe has not yet offered us a definitive answer. And yet, even without certainty, the thought itself changes the way the night sky feels. Because if the mathematics of recurrence truly allows consciousness to appear again, then somewhere in the far reaches of time, a familiar kind of awareness could ignite once more, quietly, improbably, beautifully, and it invites a final and deeply philosophical reflection. To follow that invitation, we have to let our imaginations stretch, not outward into space, but forward into time. Because recurrence, if it is possible at all, is not something that happens in the next century or the next million years. It lives in the far future, in eras so long that the human mind stops holding them as numbers and starts holding them as atmosphere, as a feeling of endless distance. And in that distance, the universe itself becomes the stage where probability, physics, and patience quietly negotiate what can happen again. The first step is to ask a question so simple, it almost sounds like a bedtime thought. How does the universe end? Not in the dramatic way of explosions and collapsing heavens, but in the slow way, the way most cosmic things happen. With time and thinning and cooling. With a gradual loosening of structure until the universe becomes more spread out, more diluted, more quiet. One of the leading ideas for the long-term fate of the cosmos is a kind of fading called heat death. The phrase sounds theatrical, but the concept is gentle. It's the idea that if the universe continues to expand, and if energy continues to spread out and become less usable, then over unimaginable spans of time, everything trends toward equilibrium. Differences in temperature even out. Concentrated energy becomes diffuse. The engines of change lose their fuel. In that scenario, the universe does not die like a creature. It relaxes, it unwinds, it drifts toward a state where nothing much happens, not because the laws of physics stop working, but because there's no longer enough free energy to do anything interesting with them. And underneath that picture is a quiet principle that has guided our understanding of time itself, entropy. Entropy is often described as disorder, but a more precise way to feel it is as the spreading out of possibilities. Energy starts in clumps, in gradients, in useful forms, and entropy is the measure of how those gradients flatten. A hot star beside cold space is a gradient. A chemical reaction releasing stored energy is a gradient. Your own body, maintaining structure and thought, is a gradient, ordered, sustained by the constant flow of energy. Over cosmic time, entropy tends to rise, not as a moral statement, not as a curse, but as a statistical drift. There are vastly more ways for energy to be spread out than for it to be concentrated. So, in the long run, the universe tends to move from special states to ordinary ones. But what is long run in cosmology? It's the kind of time where familiar milestones lose meaning. Stars like the sun live for billions of years, and that already sounds endless compared to a human life. Yet even that is only a brief chapter in the universe's full story. After the last stars burn out, there may still be eras when remnants persist, white dwarfs cooling into black dwarfs, neutron stars slowly losing their heat, black holes patiently evaporating through Hawking radiation. In a process so slow, it makes the age of the universe so far seem like the first breath of a much longer exhale. In these future eras, the cosmos becomes a museum of its own history. Not frozen, not static, but so slow and dark that change becomes rare. The universe becomes older than any structure it once held, and time stretches into a kind of quiet infinity. And if time truly stretches that far, then even a universe approaching heat death becomes interesting again. Because when you are given enough time, even the rarest events can start to matter. To see why, we have to look into what seems like the emptiest thing imaginable: empty space. In everyday life, emptiness is absence. A quiet room, a blank page, a dark sky between stars. But in modern physics, vacuum is not nothing. It is not a true void. It is a restless background, woven from quantum fields that never fully settle down. Even in the deepest intergalactic darkness, where no atoms drift and no photons pass for ages, quantum theory says that the field's underlying realities still fluctuate. Not because they want to, not because the universe is nervous, but because uncertainty is built into the way nature works at its smallest scales. In quantum mechanics, you cannot pin down every property of a system with perfect precision. And that fuzziness is not simply ignorance, it is part of the structure of reality. So the vacuum is not a dead stage waiting for actors. It is a stage that subtly ripples, even when no one is performing. These ripples are called vacuum fluctuations. They are not always directly observable as particles you can catch in a jar, but they are real in their effects. They contribute to measurable forces like the Casimir effect, where two uncharged plates placed very close together in a vacuum experience an attraction, as if the emptiness between them has a kind of pressure. In the language of quantum fields, particles are excitations, little localized pulses of the field, and fluctuations are the field's tendency to briefly stir, to momentarily form patterns that resemble particles, then vanish back into the background. Sometimes this is described as virtual particles popping in and out of existence. That phrase is an imperfect metaphor, but it points towards something profound. Even when the universe grows cold and empty, it may never be perfectly still. And this matters for recurrence because it hints at a mechanism for surprise. If the far future is not a perfectly frozen silence, but a landscape where tiny fluctuations forever appear, then the universe retains a kind of ongoing creativity. Not the creativity of living worlds and bright galaxies, but the faint, statistical creativity of a quantum sea that never fully rests. With enough time, fluctuations are not just small wiggles, they become in principle a source of rare events. A fluctuation could produce a particle, a cluster of particles, a brief pocket of higher energy. In some speculative discussions, fluctuations in a de Sitter-like universe, one dominated by a constant dark energy, could even, in extraordinary circumstances, produce complex structures. Not often, not easily, not in any way that resembles the steady, fertile cosmos we know now. But if time is long enough, not often can become eventually. And this is where cosmology begins to offer models that feel almost like ancient myth translated into mathematics. Models where the universe does not simply begin and end once, but persists, cycles, or constantly spawns new regions of itself, like a never-ending cosmic tide. Some theories suggest the universe may last indefinitely, not just for a very long time, but without a final page. Expansion continues, space keeps stretching, galaxies drift farther apart, the observable universe becomes lonelier. Yet the underlying space-time does not run out of time. Recurrence is no longer only a question of what the universe does in its bright youth. It becomes a question of what the universe does when it has all the time in the world. One idea is cyclic cosmology, the possibility that the universe goes through repeated phases, expansion, cooling, and then some kind of transition that leads to a new beginning. There are multiple versions of this, each with its own physics. Some imagine a bounce, where contraction halts and reverses. Others imagine brains colliding in higher dimensional space, triggering new hot beginnings. Some explore ways the universe could reset conditions without a singularity, turning the end into the seed of the next start. The details are complicated, and the evidence is still debated. But as a conceptual landscape, cyclic cosmology does something important. It replaces a one-time cosmic story with a repeating one. And in a repeating story, the question of you becomes less like a miracle and more like a refrain. Another idea, even stranger in its calm way, is eternal inflation. Inflation is the theory that the early universe expanded extremely rapidly in a tiny fraction of a second, smoothing and shaping the cosmos we see today. Eternal inflation takes that early burst and extends it, not as a single event, but as an ongoing process in which some regions stop inflating and form universes like ours, while other regions continue inflating, producing new bubble universes again and again. In that picture, the cosmos is not one universe, but a kind of multiversal landscape, where space is forever birthing new pockets of reality. Each pocket may have its own history, perhaps even its own physical constants. And while we cannot yet confirm such a scenario, it offers a powerful implication for recurrence. If there are endlessly many regions, then the number of opportunities for any particular arrangement of matter and any particular story of life explodes beyond ordinary intuition. Even without invoking a multiverse, the mere idea of eternal time changes the game. Because recurrence is not necessarily about the universe trying again in a purposeful way. It is about the universe having enough chances for the improbable to happen somewhere, sometime. In a cyclic model, the universe may repeatedly pass through star-forming eras, creating fresh stages for complexity. In eternal inflation, new cosmic regions may constantly arise, each with its own roll of the dice. In an endlessly expanding universe with a stable vacuum, quantum fluctuations may provide a faint but permanent background of novelty. Different mechanisms, different speculations, but a shared theme. The cosmos may have more time than we can comfortably imagine. And as it does, then the far future is not simply the end of everything. It becomes a new kind of environment, one that is darker, colder, and quieter, but not necessarily devoid of events. To feel this future, it helps to travel into what astronomers sometimes call the post-star era. This is the epoch after the universe's bright star-filled youth. Today our night sky is rich with light because we live during a relatively short-lived window when stars are common and galaxies are busy. Star formation is already slowing. The universe is about 13.8 billion years old, and it will not remain this luminous forever. In the distant future, galaxies will exhaust much of their gas. Without fresh fuel, fewer new stars will ignite. Existing stars will age and die. Some will swell into red giants and shed their outer layers. Some will explode as supernova. Many will end as white dwarfs, dense Earth-sized embers that glow with leftover heat and slowly cool. As time stretches further, even the smallest red dwarfs, stars that sip their fuel slowly and can shine for trillions of years, will eventually fade. The sky will lose its familiar sparkle. The grand spiral arms of galaxies will be less vibrant, then dim, then mostly invisible. What remains will be stellar remnants, white dwarfs, neutron stars, black holes, and scattered particles drifting through expanding space. The physics of this dark universe is not the physics of sudden endings. It is the physics of long decay. Orbits change. Objects can be ejected from galaxies through gravitational encounters. Over immense times, even stable systems can be disrupted by rare interactions. The universe becomes a thin, cold place where matter is sparse and encounters are infrequent. And yet, even here, the story may not be completely still. Because if quantum fields remain, fluctuations remain. If black holes exist, they radiate, imperceptibly at first, then after inconceivably long times, more noticeably, until they evaporate. If particles remain, they continue to move, to scatter, to feel the subtle pull of gravity. The post-star era is not the end of physics. It is simply the end of the universe's easy brightness. It is darkness with a pulse, so slow it can be mistaken for silence. And within that slow pulse, we can begin to imagine matter rearranging across eternity. In the everyday world, patterns are made quickly. A gust of wind stirs leaves, a river carves a channel, a brain forms a thought. But in the far future, pattern making becomes a matter of rare coincidences. Particles are too spread out for frequent collisions. Energy gradients are small. Complexity is harder to sustain. Still, particles do not stop existing simply because the universe is old. They continue moving. They continue obeying the laws of quantum mechanics and relativity. They follow probability distributions. They wander through phase space, the vast catalogue of all possible configurations matter and energy can take. And in a system that persists indefinitely, random processes do something strange. They explore. Given enough time, a random walk does not just drift. It visits, it returns, not necessarily to the exact same place in a simple way, but it samples possibilities again and again. In finite systems with conserved energy, there is a mathematical idea called Poincaré recurrence, the notion that a system will, after a sufficiently long time, return arbitrarily close to its initial state. Now, the universe is not a simple box of gas. It expands, it has gravity, it has horizons, it may have infinite degrees of freedom, so we have to be careful with direct analogies. But the spirit of recurrence remains a haunting guide. If the number of possible configurations is limited in some effective way, and if time is unbounded, then revisiting configurations becomes not just possible, but expected. Even when the number of configurations is astronomically large, so large that the recurrence time dwarfs anything we can meaningfully write down. Eternity has a way of making the impossible feel less impossible. Think of shuffling a deck of cards. There are about 8 times 10 to the 67 possible orders. If you shuffle once per second, you will never see the same order again within the lifetime of the universe so far. It's not even close. But if you can shuffle forever, and truly forever, then repetition becomes unavoidable. Not because any one shuffle aims for a previous order, but because the space of possibilities, though huge, is still finite. Infinity does not care about huge. In the far future cosmos, the deck is the arrangement of particles and fields. The shuffle is the natural evolution of the system. If the system keeps going, and if it keeps sampling states, then rare patterns that resemble past states, can, in principle, reappear. And here, the idea of you living again becomes less about destiny and more about combinatorics. Less about a soul returning and more about whether the universe, given enough time and enough trials, recreates a structure that is functionally the same, a pattern of matter that supports thought, a configuration that encodes memory-like structures, personality-like dynamics, the quiet inner feeling of being someone. It sounds unbelievable, and in ordinary timeframes it is. But the conversation changes when the timeline becomes so long that unbelievable is no longer the same as never. This brings us gently into the probability landscape of the future. Probability is often misunderstood as a measure of how much we want something to happen or how likely it feels. But in physics, probability is a map of possibilities. It tells us, if a process repeats enough times, what outcomes dominate, and what outcomes remain rare but not forbidden. And the most important twist is this: infinite time is not just more time, it is a different category of time. In finite time, rare events can be safely ignored. A probability of 1 in 10 to the power of 40 may as well be 0 if you only have a few billion years. But in infinite time, the arithmetic changes its mood. If an event has a non-zero probability of occurring in a given interval, and if the number of intervals is unbounded, then the expected number of occurrences can grow without limit. In certain idealized processes, the event becomes statistically inevitable, not because the universe guarantees it in a personal narrative sense, but because the mathematics of endless trials overwhelms the smallness of the chance. This is where the future becomes a landscape, not a line. A terrain of branching possibilities, where the rarest valleys still exist, and with enough wandering, even the deepest valley may be visited. Of course, cosmology adds complications. The universe may expand so fast that regions become causally disconnected. There may be horizons limiting what can influence what. The vacuum may be metastable, potentially decaying into a different state. Quantum gravity may alter our expectations. We are not holding a final complete theory in our hands. But as a philosophical and mathematical exploration, the principle remains mesmerizing. If the cosmos provides endless opportunities for rearrangement, whether through cycles, through inflationary spawning, through fluctuations in a persistent vacuum, or through the slow, ceaseless motion of particles, then certain structures may eventually reappear. Not frequently, not on a schedule, not in a way that makes the universe feel like it is repeating the same day over and over. But somewhere, sometime, in some distant chapter of reality, a familiar kind of organization could bloom again. And it may not look like Earth. It may not orbit a yellow star. It may not be made of the same atoms arranged in the same chemistry. But if recurrence is about patterns that implement experience, patterns that create a point of view, then the details may be less important than the structure. The question becomes less, will your exact life replay, and more, can the universe produce a state that is, in the only way that matters from the inside, you again? In an eternal cosmology, the probability landscape is not only about what is likely, it is about what is allowed. And what is allowed, given unlimited time, can become unavoidable in a cold statistical way. Yet even as we talk about inevitability, the mood of this idea remains strangely quiet, because inevitable here doesn't mean soon, it doesn't mean comforting, it doesn't mean you can plan for it. It means that the universe, left alone with its laws and its endless patience, might eventually stumble upon the same song twice. In the bright era of stars, the song is loud and full of instruments, galaxies spinning, planets forming, life evolving through deep time. In the dark era after starlight fades, the song becomes almost silent, but the underlying rhythm may continue, faintly, through fluctuations and rare rearrangements. And so the cosmic cycle of existence is not necessarily a perfect circle. It may be a spiral, or a branching tree, or an endless ocean with occasional waves that resemble one another. But the core idea is the same. If time does not end, then the story does not have to end in the way we usually imagine. The universe might become a place where the improbable is not a one-time miracle, but a recurring whisper, so rare that it feels like myth, but not a myth forever beyond reach, yet so persistent across eternity that it becomes part of the statistical fabric of reality. And as we let that thought settle, as we picture the far future's dim galaxies and cooling remnants, as we imagine empty space that is not truly empty and time that does not run out, we begin to sense that recurrence is not only a scientific question, it is a mirror. Because after traveling through mathematics, cosmology, and consciousness, we arrive at the quiet philosophical question that began our journey. And it is here, in the hush after all the equations, that we can finally return to the original question, not as a dare to the unknown, and not as a wish whispered into the dark, but as a calm inquiry placed gently into the hands of physics. Could you, in some meaningful sense, live again? The question sounds like it belongs to myth, like it should be answered by prophecy, or by faith, or by some ancient story told beside a fire. And yet, the strange thing is that it can also be approached through the language of matter and energy, through the patient logic of systems that evolve over time, through the quiet insistence of mathematics when it is allowed to run for long enough. Recurrence, in its most careful form, is not a promise, it's not a guarantee. It's a conditional statement made by the universe, written in the ink of physical law. If a system is bounded, if it has only so many possible states it can visit, and if it is allowed to move through those states without ending, then, given enough time, it tends to revisit what it has already done. Not because the cosmos is sentimental, not because it wants to repeat itself, but because when there are finite arrangements and endless moments, repetition becomes less like an accident and more like an inevitability. A deck of cards shuffled forever will eventually return to an earlier order. A molecule in a sealed container will eventually drift through configurations that resemble its past. A complex dynamical system, if truly confined and stable, may circle back near its starting point, even if the path it takes is unimaginably tangled. And when we apply that kind of reasoning to the largest system we know, the universe itself, the idea becomes both breathtaking and unsettling, because it suggests that even the most intricate arrangements of matter, even the delicate choreography that produced a living mind, might not be a one-time event in the full span of cosmic time. This is where the thought becomes tempting to spiritualize, to turn it into destiny, to wrap it in mysticism. But the origin of the idea, at least in this form, is not mystical at all. It emerges from the cold elegance of statistical mechanics, from the behavior of particles and probabilities, from the way entropy and phase space and time interact. It emerges from the same physics that describes heat flowing through a room, and stars burning through their fuel, and atoms colliding in the dark between galaxies. If there is a mystery here, it is not an occult one, It is the mystery of how far the ordinary laws of nature can go when the clock is allowed to keep ticking, long after our imaginations grow tired. And now, with that original question resting quietly in front of us, we can soften our focus and look at what you might mean in a universe that is constantly rearranging itself. Because one way to approach the possibility of return is to stop thinking of life as a fixed object and begin thinking of it as a pattern, a temporary luminous pattern formed by matter and energy, held together for a while by chemistry, by structure, by information. In a storm, a spiral appears in the clouds. It has a shape, a boundary, a motion. You can point to it and say, there it is, and yet it is not a thing in the way a stone is a thing. It is an arrangement, a sustained behavior of air and water and heat. And then the storm shifts. The spiral dissolves, not because something killed it, but because the conditions that supported it changed. In the same way, a flame is a pattern. A flame can vanish and later another flame can appear elsewhere. It is not the same flame, but it is the same kind of structure, the same dance of oxidation and heat. Life, in the language of physics, can be seen as this kind of phenomenon too. A structured flow of matter, a stable, self-maintaining pattern that persists by exchanging energy with its surroundings. A local pocket of order, not in defiance of entropy, but because entropy allows it, because the universe can produce islands of complexity while still increasing disorder overall. You are not made of rare substances. You are made of common atoms, doing uncommon things for a while. Carbon, oxygen, hydrogen, nitrogen, trace elements scattered like seasoning through the recipe of biology. Atoms that were forged in stars and scattered across space, later gathered into dust, then rock, then oceans, then cells. And for a brief span, those atoms become organized into a pattern that can sense itself, that can remember, that can wonder. Then, eventually, the pattern loosens, the structure collapses, the atoms continue, but the arrangement changes. And that is the crucial shift in perspective. Because if life is a pattern, then the question of recurrence becomes the question of patterns returning. Patterns can emerge, patterns can dissolve, patterns can reappear. On Earth, evolution has produced similar solutions again and again. Eyes, wings, streamlined bodies. Because the space of possibilities has attractors, tendencies, pathways that are easier to fall into than others. In chemistry, molecules self-assemble into forms that are stable under given conditions. In physics, systems settle into states that minimize energy. In mathematics, random processes still generate repetition when the number of trials becomes enormous. So it is not strange, in principle, to imagine that the pattern called a human life could occur more than once in a universe that has enough time, enough matter, and enough opportunities for structure to arise. The deeper question is not whether patterns can recur. They can. The deeper question is what it would mean if a pattern like you, with your specific memories and inner life, were to appear again. This is where physics begins to blur into philosophy, not because physics becomes weak, but because the concept of meaning enters the room. If recurrence is possible, what does it mean for the self? If somewhere, somewhen, the same configuration of matter and energy arises, down to the precise arrangement of synapses and molecules, would that be you again? Or would it be someone indistinguishable from you, a perfect copy, a new candle lit from the same blueprint of flame? From the outside, an exact recurrence would look like a return. The same body, the same face, the same tendencies, the same memories, at least at the moment of formation. But from the inside, the question becomes more delicate. Because individuality, as we experience it, is a continuous thread, a feeling of being carried from one moment to the next, a sense of, I am the same one who was here a moment ago. Recurrence, if separated by vast stretches of time, would not feel like continuity. No tunnel of consciousness traveling through empty ages. And yet, the thought still lingers, because what is the self, really, except the pattern? If the pattern returns, perhaps the self returns, in the only way nature ever allows anything to return. Not as a preserved object, carried intact through time, but as a structure that happens again. Some philosophies would find comfort in that, others would find it unsettling. Some would say that without continuity, it cannot be you. Others would say that if every detail is the same, then you is simply what that detail produces. And perhaps both intuitions are reaching to something true. Maybe recurrence does not diminish individuality, but reframes it. Maybe being an individual is not about being unrepeatable. Maybe it is about being a particular expression of the universe at a particular moment, a particular arrangement that for a while experiences itself. Humans have always tried to interpret cosmic possibilities through human emotions. We look at the sky and we see stories. We look at time and we see fate. We look at chance and we see intention. So, when we hear that the universe might repeat patterns, we instinctively ask what it means for us personally. We want it to be a message. We want it to be a verdict. We want to know whether recurrence is a gift or a trap or an illusion. But the universe does not speak in that kind of language. It speaks in probabilities. It speaks in constraints and freedoms, in the number of possible arrangements and the time available to explore them. If recurrence happens, it does not happen for us. It happens because the universe is the kind of place where, under certain rules, certain patterns are permitted, and time is patient enough to try them more than once. And that brings us to another quiet thought, one that feels almost comforting in its strange neutrality. A universe that never truly forgets. Not in the sense that it keeps a diary or stores memories in a celestial archive, but in the sense that the laws of physics do not erase the possibility of a pattern returning. Even when a structure dissolves, the ingredients remain. The particles do not vanish. They move on. They mix. They collide. They become parts of other things. In many physical descriptions, information is not easily destroyed. It can be scrambled, dispersed, entangled with the environment, becoming effectively unreachable, but not necessarily eliminated from reality. A broken egg cannot be unbroken in practice, because the information about its orderly state has been scattered into microscopic correlations across the room. The air molecules have carried away the details. The floor has absorbed them. The world has moved on. And yet, in principle, the laws that govern those molecules are reversible. The story is not erased. It is simply written in a language too fine for human hands to gather back together. The cosmos is always doing this, always rearranging. Stars fuse simple elements into heavier ones, then die and scatter them. Planets form, collide, fracture, reassemble. Molecules drift through interstellar clouds, freeze into comets, melt into oceans, rise into breath, fall into soil. Nothing is still for long. Even the things that feel permanent, mountains, continents, the shape of the galaxy, are temporary patterns on a long enough timeline. So if there is a sense in which the universe remembers, it is not through nostalgia. It is through continuity of law. The same rules apply everywhere, and for as long as the universe remains a universe, the same possibilities remain open, again and again, as matter explores its options. And in that way, the cosmos becomes an ongoing experiment, one without a final report, one without a single observer watching from outside. A vast, self-running laboratory where particles and fields test configurations across unimaginable spans of time. Sometimes the experiment yields simplicity, thin gas, cold darkness, slow drift. Sometimes it yields complexity. Stars, chemistry, storms, oceans, and sometimes, at least here, at least once, it yields a living pattern that can ask questions about its own return. When you look at recurrence from that distance, a certain fear can soften, because the fear often comes from imagining recurrence as a demand, like a cosmic obligation to repeat, or a sentence to relive. But physics does not demand, it describes. And the act of describing can be strangely calming, because it replaces the sharp edges of existential dread with the smooth contours of curiosity. Instead of asking, will I be tracked in an endless loop, we can ask, what kinds of universes allow repetition, and why? Instead of asking, am I destined to return, we can ask, how does matter behave when time becomes vast? In cosmic perspective, your life is not small in the insulting way we sometimes mean when we say small. It is small in the way a delicate pattern is small compared to the ocean. And yet it is still real, still remarkable, still rare enough, at least in our experience, to be precious. You are part of cosmic history, not separate from it. Your atoms carry the signature of old stars. Your body is a temporary arrangement of ancient material. Your thoughts are what happens when the universe organizes itself into a form that can reflect. And scientific uncertainty, rather than being a void, can become a kind of beauty. Because uncertainty means the story is not finished. It means there are still chapters the universe has not revealed to us. It means our understanding is a candle, not a floodlight, bright enough to see nearby shapes, dim enough to leave the horizon mysterious. We do not know the final architecture of time. We do not know whether space is truly infinite, or whether it loops back on itself in ways we cannot yet detect. We do not know whether the universe will expand forever into a cold thinning, or whether something will change in the deep future. We do not know whether recurrence is a strict feature of reality, or a delicate possibility that depends on conditions we have not confirmed. And yet, even without certainty, we can rest in the wonder that the question can be asked at all, and that the answers, whatever they are, emerge from the same quiet laws that shape starlight and snowfall. Now, let your mind drift to the long future. Not the future of years or centuries, the future of eons. Imagine atoms, those small, sturdy building blocks, continuing their endless motion. Vibrating, drifting, bonding, breaking, colliding. Atoms do not grow tired. They do not carry regret. They do not cling to former shapes. They simply follow the rules. Over time, the atoms in your body will scatter into the world. They will become part of other organisms, other landscapes, other air currents. They may sink into stone, then rise again in volcanic breath. They may pass through oceans, then freeze into ice, then evaporate under a distant sun. And if the universe lasts long enough, those atoms, or atoms like them, will pass through countless configurations. The same carbon that once helped your neurons fire could, in another era, become part of a leaf on a different world, or the dust around a newborn star, or the slow chemistry of a planet that has never known life before. In the farthest futures, if stars burn out and the cosmos grows dim, matter will still move. Slowly, yes, but it will move. Particles will still interact. Quantum fields will still fluctuate. Given enough time, even rare events become inevitable. Given enough time, even improbable arrangements can occur. This is one of the strangest truths that probability teaches. When the number of trials becomes vast enough, the unlikely stops being exceptional. It becomes part of the landscape. And so, in the long, slow rhythm of the universe, recurrence becomes a kind of cosmic poetry. Not poetry written by intention, but poetry written by scale. A rhythm made of atoms and time. A dance in which no step is forbidden forever. In this dance, stars are not monuments. They are phases. Galaxies are not eternal cities. They are swirling patterns in a gravitational sea. And life, your life, is a brief but astonishing movement in the choreography. A moment when matter becomes aware of its own motion. When you think of it this way, recurrence is not just about you. It is about the nature of change itself. It is about the way the universe explores what it can be. The way it tries forms, dissolves them, and tries again. Sometimes the same kind of form appears in different places. Spirals in hurricanes, spirals in galaxies, branching in rivers, branching in blood vessels. The universe loves certain shapes, not because it chooses them, but because the laws of physics make them efficient, stable, or likely. And perhaps, among the shapes the universe is capable of, the shape of a conscious life is one of them. Perhaps consciousness is not an accident balanced on a knife edge, but a possible outcome that emerges when complexity crosses a threshold. Or perhaps it is extraordinarily rare. Perhaps it happened once in our region of the cosmos, and may never happen again nearby. We do not yet know. But as the future stretches outward, beyond the lifespan of civilizations, beyond the lifespan of species, beyond the lifespan of planets, the question remains open, floating like a distant star. If the universe keeps going, if matter keeps rearranging, then the dance continues. And if the dance continues, patterns may return. Not with fanfare, not with announcement, quietly. Now, in these final moments of our journey, you can let the question settle into something softer than an argument. You can treat it as an invitation. An invitation to feel your existence as part of a vast process that doesn't revolve around you, and yet includes you completely. You are not outside the universe looking in. You are the universe in one of its temporary forms looking at itself. And that is already strange enough to deserve a long, calm pause. If recurrence is real, it does not need to be a doctrine. It can simply be one more way the cosmos expresses its depth. A possibility that reminds us how large time might be, how many chances reality may have to explore itself, how many versions of now may unfold across the full span of existence. You do not need to decide what it means tonight. You do not need to force the mystery into a neat conclusion. Wonder is allowed to remain open. In fact, wonder is often at its most peaceful when it is not demanding certainty. So as you rest with this thought, imagine the universe continuing on, patient, indifferent, creative in its own unconscious way. Imagine matter drifting through darkness, gathering into clouds, collapsing into stars, scattering again. Imagine worlds forming and breaking, chemistry blooming and fading, patterns rising and falling like slow waves. And somewhere in that immense unfolding, whether near or unimaginably far, whether likely or vanishingly rare, the same physics that shaped you once may shape something like you again, not as a miracle, not as a promise, as a possibility written into the quiet mathematics of existence. And somewhere in the distant future of the cosmos, among countless rearrangements of matter, a familiar pattern might quietly appear again.